Philine van Vliet from the Ecole Normale Supérieure, who's going to talk about consequences of symmetry breaking on conformal defect data.
Thank you very much for the introduction, and thank you for the invitation to speak here. So I'm going to talk about work that came out this September together with Bastien Giraud, PhD student in Paris, and Miguel Paulos. And in the end, there's some outlook and some example that is related to some work in progress that we have with Gabriel Bliard, who has already left physics but has made important contributions already in the beginning of this project, with Julius, who's here in the audience, also with Miguel Paulos, and with another PhD student, Noé Suchel, also at ENS in Paris. So I want to talk about conformal defects today. So it's gonna be nice. We're gonna see some elements of things that Marco already said in the talk before. And let me just remind you one more time that conformal defects break the bulk conformal symmetry group SOD plus 1,1 to a conformal subgroup on the defect. So the defect is going to be p-dimensional here. And we're also going to preserve rotations around the defect. So it's important that we're looking at conformal defects and not topological ones, because it's going to be the breaking of the symmetry that is going to give us constraints on correlation functions of both bulk and defect operators. And I'm also going to consider just a single defect, so there's no fusion between defects or anything, but with insertions of different numbers of local operators. And in principle, it's going to be for arbitrary dimension of codimension. However, I'm going to focus a lot on one-dimensional defects in this talk. So today, it's going to be mostly about applications of these constraints. So first, I will derive these constraints, and I want to talk about applications for the numerical conformal bootstrap of line defects, and there will also be some perturbation theory. So for some of you who have studied the program intensively and have read every abstract carefully, you might have noticed there's also a talk tomorrow by Peter Klavchuk. And this is based on similar work that they are doing together with Nadav Drucker and Ziwen Kong. That is, they have a similar, they find similar constraints, but with a slightly different derivation. And in particular, they also consider the case where we have some anomalies that appear. So yesterday we heard a lot about anomalies. If this is what you want to kind of also get out of these constraints, then you should definitely also see, pay attention at Peter's talk tomorrow. So even though the constraints are going to be roughly the same, the applications are going to be very different, and it's going to be two hopefully very nice talks. So motivation-wise, Marco motivated defects, but I was very happy that this might be the one conference where I don't have to justify why I'm working on defects. And also the fact that there's now 2 talks about these constraints already indicates this is a hot topic. There's also, around the same time as our paper, this paper by Jake Belton and Ziwen Kong that appeared. So yeah, this is all the motivation I think I need at this moment. So we're going to derive some constraints coming from the breaking of these symmetries. And the way we derive these constraints is a bit reminiscent of what happens in QCD when you have spontaneous symmetry breaking. So in QCD, this will lead, as everyone knows, to massless Normal-Goldstone bosons. And you can also derive some rules on scattering amplitudes of these Goldstone bosons, which are the pions. And this was already done in the 60s, and it leads to famously the Adler zero, which indicates that in the soft limit, these scattering amplitudes vanish. And it was later on generalized by Weinberg to the soft pion theorems. And we already saw them 2 days ago in Raju's talk, briefly flashed. You can also derive them not only for pions, but for photons, gravitons, phonons, everything. And in our case, the way that these were derived is going to resemble the way that we derive our constraints for conformal defects. So the difference is here, of course, we don't have spontaneous symmetry breaking, we have an explicit defect in the CFT. And we also don't really have this notion of of softness. So instead of the massless Namu-Goldstone bosons, we will get some protected operators like displacement and others that I will mention in a second. So some of these constraints were already known. I've put a few papers here. I have a more extensive detailed list at the end. And some of these were derived for defects specifically, others were more for conformal manifolds, and they were also derived using a variety of techniques and a variety of motivations. So what we want to do here is we want to present one framework to derive all of these in the literature and also add some new ones. So that is the goal for the first part. And I also want to stress that there's an interplay that arises between conformal bootstrap, these constraints, integrability, SUSY localization, all topics that we have have already seen in this not only this conference but this whole program. Okay. So the plan is to first derive these constraints. We'll start with only operators on the defect, and then we'll inject the bulk operators into this setup. And on the way, I will discuss 3 examples. And because of time, I will probably go through them a bit quickly. But if you have some questions, please don't feel feel free to interrupt me at any time.
Just a quick question. So
yes.
This is symmetry. You refer to the internal symmetry. Do you include space-time symmetry?
Yes. So this is okay. This is a few slides further, but yeah, we'll see that there's different symmetries that you can consider: flavor, conformal symmetry itself, and also supersymmetry if you want to. Yeah. Okay. Okay, so let's start at the very beginning just to set some notation because, okay, this is in general known. So if we have some symmetry G, then we have an associated conserved current that we denote by J, and some conserved charges that are given by this integral over this hypersurface sigma. And they also satisfy some algebra. And we denote the transformation of local operators O in this way, in some representation R of this symmetry group. So now if we break the symmetry from G to H, we can split these charges into broken and unbroken charges. And the unbroken charges will denote by S, and the broken ones will have this little tilde on top. And necessarily these unbroken charges, which are preserved by the defect, they will satisfy, they will close up on themselves, so they satisfy their own algebra. While the broken ones can kind of rotate on another broken charge, but also on an unbroken charge. And we can pick our bases such that if we have this combination of charges, unbroken and broken, that they only rotate onto a broken charge. That's just a choice that we made that simplifies some expressions. So now, as we've seen, we are looking at conformal defects, so we break it from SOD plus 1,1 to SOP plus 1,1 times SOQ. But we can also have additional flavor symmetries in the bulk, which are these groups G that get broken to some H. And as I said before, we can also have supersymmetry, but this is a bit harder to write down in general, so you have to just imagine it. And this leads to a set of broken Ward identities. So for the flavor current, for the stress tensor, and for the supersymmetric current. And each of these leads to a protected operator on the defect. So in order, these are the tilt, the displacement that we already saw in Marco's talk, and a third fermionic operator that had no name before, and we called it the displacino. And all of these have operators that are, or have dimensions that are related to the dimension of the defect. So P, it's going to be a marginal defect operator, P plus 1 and P plus a half. Indeed. So now what we want to do is we want to...
Sorry.
Yes.
What about the special conformal transformations? So these don't give new fields.
So these are encoded in this conformal killing vector that we have here. So yeah, so we will see that the generators of special conformal transformations also give constraints on the on the operators, on the displacement correlators. Yeah.
Sorry,
Yes.
small question. So do you, in this definition or integral, how do you deal with this intersection between the topological operator and the defect?
Yes, so we will see this later on. I will work out these integrals specifically. So we're going to use the bulk to defect OPE that also Marco described in his talk before.
That was not included in the integral. Integral does not include an intersection.
So this integral is on a hypersurface that intersects the defect. So I will have some pictures later on. Maybe if you, it will become clearer then if I do it explicitly, and then you can ask again if it's still not clear. Okay, so now we want to derive constraints on correlation functions. So we start with a correlator of an arbitrary number of bulk fields, which we will denote by x. And we insert, first we are going to insert one broken charge. And in this talk I will mostly consider the tilt because it's just easier with, in terms of formulas. But I will make some remarks about the displacement on the way. So we insert a charge, and on the right hand side we get the action on, or the transformation of these bulk fields.
Sorry, can I ask a question?
Yeah.
It's just silly. So I've seen some oscillation between displacino and tiltino. Why did you settle on what?
Yeah, so we've had this discussion ourselves as well. I think, so displacino, because our reasoning was that you are kind of breaking supersymmetry, so the generators are going to be the super translations in superspace. Okay. And this to us was more similar to the displacement. And there's also a nice ring to this name that we also really like. But okay, that was secondary to this first one. Yeah. Okay. So we're gonna consider this correlation function, and we're gonna replace this broken charge by the broken wart identities that we just saw before. So this would become the tilt, and we're gonna have this integral. And this integral is going to be over half of the space. So we insert the charge at some hypersurface that is drawn here, that intersects this defect here, and the integral is over this whole half space. And we can either take the integral over the upper half or the lower half. We're free to choose, and this should be equivalent. And we either pick up the contributions of all these bulk operators that are denoted here, or we just have the vacuum. So this gives this identity that we see here. And this means that you can kind of combine these two integrals together, and you get this very nice simple identity that is written here below. And importantly, we see that this t, which is just an arbitrary location where we insert this hyperplane, drops out. And this is as we would expect. So in the end, the identities are going to be independent of these. So now this is for one charge, and okay, in analogy to the QCD theorems, we will call this the defect soft identity. And now we can also think what happens if we insert two charges. So we insert this commutator of two broken charges, and we see that it rotates onto an unbroken and a broken one. And we can do the same thing. Yes?
If we consider specific theory, QCD, do we need to consider anomaly here?
No, we don't need to consider... Sorry, what if you...
If we consider specific theory, QCD, do we need to consider anomaly in your correlators?
For certain theories, you would need to consider anomalies if they are there.
Yeah, so
but for the examples that we will see, they are not going to be...
But for QCD, do we need?
I think that depends on the defect and the amount of the correlation functions you are considering. This is not... I cannot make a general statement yet.
Okay, so in this sense, your formula may not be applied to QCD.
Well, it depends on what you're looking at. Yeah, so, okay, but for these things, I think Peter will make it clear tomorrow what are the exact things. Yes?
In the previous slide, I'm just curious, can you also read it the other way around? Like if you have a protected operator, let's say the tilt, and you integrate, can you guess what is the charge, the conserved charge that this corresponds to?
Sorry,
It
what
is
is?
that equation? Okay, you have the integral of the tilt, of the expectation value of the tilt with this bunch of operators
Yes.
is equal to the charge active on these operators.
Yes, yeah.
Can you also and we started by the action of the charge on these operators, and we know that this
If you can reconstruct the
if I have a protected operator
yeah.
and I integrate, can I see that it's a conserved charge if I didn't know the conserved charge before?
So, okay, in general, this is, I would say, in practice, this is going to be almost impossible to do, right? Because you're going to get the integral of some correlation function, so this is going to give you some number, some quantity. So then you would have to compare it with something, say like, oh, it's exactly this quantity, and then, oh, I know that this quantity is coming from here. I think this is hard to do in general. Yeah. Okay. So now we're back to two charges, and we can replace both of them by the integral over the tilt operator. And this gives us our second double soft identity, which is a lot more complicated than the first one that we saw. So in particular, we have now, where before we could either integrate over the upper half or the lower half, we're now forced to do both. So let me look for some chalk. So the contour that I just drew, you now should think of two charges inserted on kind of two hyperplanes that are close together. So this will be at x0 and this is x0 prime. Equals t equals t. And you're gonna have some bulk operators either to the left or to the right. And now, so this is my q s tilde and q t tilde. So now we have to kind of integrate this one to the top and the other one to the bottom, so that we don't integrate from the bottom one including the top one, because we don't know how these broken charges act on a broken charge on a bulk operator. So we know exactly how they act on the bulk operators, but not how they act on other operators. So this is why we get these two integrals, one bigger than t, the other smaller than t. And okay, the rest of the identities, or the rest of the terms, you can read off by carefully considering this identity. So this looks a bit cumbersome to work with, but we'll see that if we go to some specific examples and some applications, and especially the applications that I will talk about today, only a few terms will actually contribute and the rest will just be zero. And in particular, we have this first, well, all the terms in green are conveniently the ones that will play a role today, and the rest will just be zero. Okay, so these are the two identities that we will work with, and as for now they're quite general, so let's simplify a bit and also consider some specific correlators.
Sorry,
Yes, yeah.
in this identity, is t dropping out as well, or?
Yes, so here it's not so obvious to see, but in the end, if you compute it for 4-point functions, etc., it drops out. We also checked that if you would take the derivative with respect to t of this identity, it's zero, so it's independent of t. And
it is crucial here that you're taking them, like you drew them slightly far apart, but it's crucial that
they are very close together, yes.
Because they're not topological, these operators, so
no.
you cannot just move them.
Yeah, exactly, yeah. So it's crucial that they are close together, that is, yeah.
Okay. And since they're not topological, why? No, okay, so the fact that they obey the algebra is because you're acting on bulk operators.
Exactly.
And when t is equal, the remaining integral over the surface is the one that should sort of go away.
Yes, yeah, yeah.
Thanks.
Okay, so let's simplify, and we're gonna take just one-dimensional defects, so line defects, and we also take an extra symmetry breaking that is gonna be SON to SON minus 1, And this in particular will mean that this f here of only broken charges is 0. So this is also why, for example, this whole term immediately drops out, just by the choice of defects we consider. And let us start with deriving correlators of defect operators. So these are just operators localized on the defect, and they obey all the normal constraints of a one-dimensional CFT. In particular, their one-point functions are 0, their two-point functions are completely fixed, and their three-point functions are also kinematically fixed, and they depend on the OP coefficient that is written in red here.
Can I still ask a
Yeah.
question about
Yeah, of course.
general philosophy? So, is there a reason why you did not? So, you could have obtained a commutator with fully topological operators if you were to just enclose a few of them by a ball in the bulk
Yeah,
that doesn't intersect the defect at all, and
Yeah.
then take the commutator of two of these charges.
yeah.
Would this lead to the same constraints? It doesn't lead to constraints at all? Because it looks a bit cleaner, because now you have topological operators. For real, you don't have to check that things drop out.
I would say it probably would lead to the same constraints.
Okay.
I would guess so. Yeah.
Because the first line would give that constraint, because you're just applying the commutator of the charges on a subset of
Yeah.
operators.
Yeah. So I would say it should give the same constraints. Yeah. But okay, I haven't worked it out, so I cannot be sure. Okay. So here I've also made this normalization of the two-point function red, because normally this is not important. It's kind of, okay, you can normalize operators however you want, except that for all these protected operators, their normalization is actually a piece of defect CFT data that is non-trivial and that we want to constrain. So if this is to tilts or to displacements, this is a coefficient that we also want to look, that we want to try to find constraints on. And now we want to look at four-point functions, because as Marco showed earlier, they obey some crossing equation, and they also encode an infinite amount of defect CFT data. So the spectrum and these OP coefficients, you can all extract them from this four-point function. And in 1D, this is a very simple formula. It's just given by a function which is a function of a single variable, so a single cross ratio z, that I've written here. Okay, so in order to do this, we start from one broken charge and three bulk operators, which is going to be the current. And we take the defect of the OP of the current. We'll have the tilt operator as its first operator for small, as we bring this current close to the defect. So this one lives in the bulk, and y is the distance to the defect. So if we take y to 0, then this is going to be the leading term in this expansion. Now, if we apply the soft identity, we get the following identity on these bulk operators, and now we know how this what this right-hand side is. It's well defined, and this is a perfectly well defined integral on right-hand side. Now what we can do is we can push these operators down to the defect. So we will set all these y's, we'll set them to 0, and then we find the tilt operators in their bulk to defect OPE, and we obtain a relation on the four-point function of tilt operators. Now I say this quite simply, like, okay, we would just push them down and that's it. It's a bit more subtle. You have to be careful that these divergences, certain divergences will need to cancel. But if you are careful about that, you find this relation, and in this case, the right-hand side is just the three-point function of tilt operators, which is 0 for the examples that we consider. Okay, so we see that we get a very nice and very simple identity. So let's now do the same thing for the double soft sum rules. So we start now from two currents and two broken charges, and we do the same thing. So we write the identity, we push the bulk operators towards the defect, and we find an identity on the four-point function of tilts, where now these indices needs to be anti-symmetrized. And now we get a right-hand side that is non-trivial, And in this case, it's proportional to the 2-point function of the tilt, so it's proportional to this normalization constant. And we find that this is constraining this normalization. Now, we know that, we see here that we have this double integral because we needed to go to the top and to the bottom. But we know that this 4-point function is just a function of a single cross ratio, so we can rewrite this integral. And in terms of this cross ratio, and we find this very nice formula that now contains some log of z and log 1 minus z. And here I've split this function g that appeared in the 4-point function into the functions that correspond to the different representations of on minus 1. So this is the singlet, the symmetric traceless, and the anti-symmetric representation. And now on the right-hand side, we just have this coefficient ct. So now, starting from this multi-line double identity that we saw before, we see that we now just have a single integral over the cross ratio that we can actually work with. Okay. So in the case of the displacement, there's more generators that we have to consider. So for the tilt, we just had one, so we get two identities. But for the displacement, if you consider translations, special conformal transformations, and rotations around the defect, you'll find that you get two soft sum rules that are independent of each other, and three double soft sum rules. So three independent constraints here. And you need to, and this is not okay, there's some rewriting that you need to do, but in the end you find that these are the independent ones on the 4-point function of the displacement. Yeah.
So when you do this trick of like repeat the bulk current, you wrap around the topological operator, you get it, and then you take the OPU. Can you use that to assign a transformation rule under the broken charge to the tilt operator? Is there a...
That's a good question. We didn't think about this.
Or to the displacement?
Yeah, so maybe indeed you can derive some transformation rule just from the fact that you're allowed to do this. Yeah. Let's see. Okay, maybe if you. Okay, yeah, I'm not so sure if it's going to be like an unambiguous transformation that you can get. I can imagine starting from the 2-point function, but this gives you like a trivial relation. So for us in this case, the first kind of non-trivial relation was this 4-point function. So I don't know if this is already too complicated to really extract a single transformation rule. But yeah, it would be interesting to see if this can be the case. Yeah, thanks. Yes?
In the first line in this slide, you have an object that has 4 indices. To get to the constant Ct, you contract it with some... but this object has 4 indices. You contract it with some tensor as well. So that's this equation with no indices? Yeah,
so in this case, this f is just 1, I think.
Oh, okay.
Yeah,
okay.
so it's just a simple, but that's because we have a very simple flavor symmetry breaking that we consider. Yes, thank you. Yeah.
This 4-point function, I guess it should be related to some curvature on the conformal modulation?
Exactly, yeah, so this 4-point function was already derived by Anatoly Konechny and Vliet in 2014 in the case for a conformal manifold. And it relates to this curvature Rijkl of the, well, in this case of the defect conformal manifold. So it would be generated by the coset of On and On minus 1.
So
yeah.
Is this relation independent of that, or is it?
No, it's the same. Yeah, it's the same. Yeah, yeah. Yeah, so indeed, okay, I put the references to the end, but this would be the same as that one. This first one that we saw, this was derived by Connor Bahan, also in the case of conformal manifolds, not necessarily for defects, but you can get the same relation. And okay, for displacements and in higher D pairs, our derivation is new, but in this one-dimensional case, they were derived before. Yeah. Okay, very good. Okay, so now let's look at some applications. And what we want to do is we want to extract this defect CFT data. So the best way to do this is to take the 4-point function and expand it in conformal blocks. Because you get the sum rule over this defect spectrum and these OP coefficients of defect operators squared. And here with I just denote the same representations of ON that I had before. And again, in 1D, this is the simplification that these are just very simple hypergeometric functions that are denoted here. So in principle, you can do this. You can replace G by this expansion in blocks, and you can, work, play around a bit with crossing symmetry, and you can find the sum rule on these OP coefficients. But there's something more that we can do. We can improve this a bit and replace G by a dispersion relation. So this dispersion relation is given by the double discontinuity of this function G, and it has some kernel that is known how to work this out, but you would have to work it out, and this is what we also did in our paper. And this leads to, well, we can rewrite this sum rule, so now here we inserted the dispersion relation, and we now get a sum rule with these f's, some functionals that, and delta hat is the dimension of the defect operator. So why do you want to do this? Well, because of the double discontinuity, we now get some nice form of these functionals. Let me show it here. So they have double zeros that you can see here on all the even integer dimensions. And especially if you go close to some generalized free theory of your CFT, then the 4-point function will have double trace operators that are exactly at these dimensions. So if you want to study defects that are kind of perturbatively described by such a theory in the free limit, then here you're going to find that a lot of terms that otherwise you have to consider will be dropping out because they are exactly at these double trace or these double zero points. And there's something else that's very nice that we can do now, and that is derive some rigorous bounds on the operator spectrum just by looking. So we saw before, or we saw that this sum rule is should be equal to some constant or to 0, depending if we have the double soft or the soft identity. And if we consider now unitary theories, then as we saw before, all these OP coefficients squared are going to be positive. So we have a sum of positive coefficients that multiply a functional that is positive everywhere, except in these red regions. And this means that if you want to have something that is non-trivial, then you need to have at least a contribution coming from this red region. Otherwise, you can never satisfy this sum rule. So this means that there has to be some operator that has dimension between 1 and 2 in the OP of the two tilts. And this operator can either be a singlet or a traceless symmetric of the ON-1 symmetry. So this is a bound on the spectrum, or a constraint on the spectrum that we can derive just by looking at the shape of these functionals. And if we now consider the 4-point function of the displacements, we get a functional that is very similar, except that it now has poles both at delta equals 1 and delta equals 3. So there's two possibly negative regions that we can use, and we can have an operator either here or here. Okay, this is a first kind of constraint on the defect CFT data that we derived. And now you might wonder, okay, but what kind of defects, are there examples? Can we show that these are indeed always have some operator that lies in these regions? And okay, conveniently, all the examples that I will show you indeed have this property. So let us look at the first one. And this is the pinning field defect in the ON model. So here we have the action of the ON CFT with a scalar field phi a, where a runs from 1 to n. And we add the integral over one of these scalar fields, so we pick the direction phi1, but this is arbitrary. And we add this integral, and this will become our line defect. So we can analyze this model in 4 minus epsilon dimensions, and this defect will always stay one-dimensional, so it's always a line defect, and the bulk will change dimension. And then in the IR, it flows to some fixed point for that is given here. So the bulk, this is the fixed point of the ON CFT perturbatively in small epsilon, and the defect fixed point was computed in this paper here. So you can see that by picking out this one scalar, we indeed break ON to ON minus 1, so we have a tilt, and we're also going to have some scalar field, sorry, this should have been ahead. So some scalar defect operator phi1, and its dimension was computed up to order epsilon squared. And in this model, the displacement is given by the transverse derivative of this scalar phi1. So now we can, so we see that this operator phi1 indeed has dimension. Well, if you Padé resum it, it will be something around 1.55, so it's nicely in the middle of this region, this red region that we saw before. And we can now use our sum rule, for example, the double soft one, to extract some higher order perturbative data. So, okay, I've written it all out here. Let's go step by step. So we can compute some data at order epsilon, which is a bit of work, but it's doable. And for example, this normalization, we can compute it at order epsilon. So if we look at all the contributions that we get, is we're going to get also contributions from operators with dimension close to 2, with some anomalous dimension gamma. But all the contributions of operators with dimension 4, 6, etc., they're all going to be suppressed by these double zeros that we found in our sum rule. So we don't have to consider them here. And we do get a contribution from phi1, which has dimension around 1. And since this has a pole, or actually a double pole, it will give some 1 over epsilon squared term here. And we can add data up to order epsilon squared that will contribute to this order epsilon expression. So now we can use all the data at lower orders, either order 0 or order epsilon, to compute this order epsilon squared piece. And we find the following expression. Now this is very nice because several people have attempted to actually do the two-loop computation and compute this one, but none of us have yet succeeded. So it's very nice that we can just extract it from the sum rule, and we can check with different sum rules that it's all consistent, so we are confident that this is the right answer. And you can do the same thing for the displacement, and this was already done in this paper by Gabay, Sever, and Zong. And you find a similar expression for this one. So this is one application of these sum rules that it's very nice, straightforward to now derive some constraints perturbatively. But I said in the beginning, one of the motivations is to do numerics and to also get some non-perturbative constraints. So let's do numerics. Well, we did it, and we looked at the displacement of, or the 4-point function of displacement. So in this particular example, the bulk is two-dimensional, meaning that the displacement does not have any indices. There's no rotation around the defect. In the displacement OP, the first operator has dimension between 3 and 4. So if we go back to this thing, we assume that there's no operator here, but that the first one is appearing here. And okay, we put some gap on the second operator that appears after. This is arbitrary, and we can vary it a little bit. So now we see if we have a bound, if we bound the OP coefficient of this first operator, whose dimension we vary between 3 and 4, that if you don't impose this sum rule, you get this whole red shaded region here, which is allowed. And you can in principle pick anything, even if you put a gap on this second operator. But now if we impose this soft sum rule, then our bound immediately goes to this green one that we see here. And we now also find a lower bound that is not just 0. So now the only allowed values are going to be in this shaded green region. And with the double soft sum rule, we also now have access to a bound on the displacement normalization, while before we had no way of inputting this in a numerical bootstrap. So these are two plots that show the effect of these sum rules. And let's now go to, yes?
These plots are relevant. So if this was a boundary condition for a 2D CFT,
Yeah.
then you would know what because D would be part of the identity module, right?
Yeah,
no,
so I
there's
think in
another-
that case you have D as the first operator in your OPE, right?
Yeah, so if it's a boundary condition, yeah, it's part of the identity module, and then you have D in the OPE. So that's why I was asking, because you said delta hat cap equals greater than 3.
Yes, so in this case it's not in its own OPE. So,
Yeah, so you're assuming that this is similarly anyway.
Yeah.
You're assuming that at least you're in the interface between two.
yes,
objects.
yeah, I will, yeah, so we had a specific example in mind that has exactly these properties. But yeah, this is an assumption that is kind of the strongest assumption that we can make. If you would put, for example, the displacement first and an operator between 1 and 2, okay, it's going to be different.
But this example is compatible with a, like, I'm just asking if the bulk has Virasoro, or if your example is a long range, or some theory in which the bulk doesn't have Virasoro.
Yeah, so the example is going to be this flux tube in ADS. So there's no Virasoro in the bulk. Yeah, I didn't think about what other examples this could apply to. It could be that because of Virasoro this is not allowed. Is that what you're saying? Or?
Yeah, because with interfaces there's two primaries.
Yeah.
Well, there's the identity, and then there's a new primary at dimension 2.
Yeah.
Which, okay, some people in the audience are responsible for
Yeah.
this W, which is dimension 2. And the displacement is made out of this, so I
Yes,
don't know.
yeah.
Like it's something one can check what appears in the OPE.
Yeah, exactly. So in this case, we can check that this does not appear, and the first operator that appears is like the derivative of the displacement, and has dimension 3 going up to 4 as a function of the coupling. Yeah. Okay, very good. Nice bridge to the next example that we're going to discuss. So this is the example of a flux tube in ADS. So we saw yesterday the talk by Lorenzo about young males in ADS. So we also have young males in ADS. It's going to be 3D young males for now. And you can have some pair of Wilson lines on the boundary that generate this kind of stretched out flux tube that's in the bulk ADS. And on the boundary, this just corresponds to a one-dimensional CFT. But as we saw yesterday, as it was pointed out, this does not lead to a local bulk conformal field theory on the boundary. The bulk conformal field theory is non-local, it doesn't have a stress tensor, so you might ask, okay, but how can we derive the displacement operator? Because we just said it was defined by the word identity of the stress tensor. So in this case, it's given by the field strength F, so F is d mu a mu minus d mu a mu. And this takes the role of the displacement operator. And in this paper, they check that indeed the relations we just derived for correlators of the displacement still hold, and we can still use them. So there's two perturbative descriptions. We can either take small radius of ADS, this is going to be an expansion in weak coupling, or we can take this radius to infinity, and then you can do computations in effective string theory. So you can do these perturbative computations on both sides, and then you can do a Padé approximation to get a prediction for all couplings. And this was done by Bendegoed-Offerthaler and the people on this paper.
So
Yes.
how to do the Padé approximation to get all terms, all correlators?
You get all?
All correlators.
You do this for one, so they did this in this case for example, the OP coefficient of the displacement, and first operator. So they did it, you have to do it for each of the things that each of the observables you compute perturbatively.
Yeah, but then I remember the Padé approximation is only for the field, a field terms can give a good result. If you really do the many terms, it may give a better distribution.
Yeah, so I mean, Padé approximation it's an approximation, right? So,
Yeah. So in
Yeah.
this sense, that it's hard to know whether it's good or it's bad.
Yeah, indeed. So there's something that you might ask. You might also ask, is there like a consistent description for all values of the coupling that interpolates between weak and strong? So I forgot to mention, but here we are assuming Neumann boundary conditions. So yesterday we saw that with Dirichlet there was some trickiness. But with Neumann, you expect that this would hold from weak to strong coupling, and this Padé should be relatively good. But this is one question that you can ask, like non-perturbatively, is what we find? And you can, for example, check it with the numerical bounds that we just found.
So in this sense, I can say that there are methods that I just can understand whether it's good case by case.
Yeah, so, I mean, for now, as I understand Padé, indeed, you have to, there's also, if you do Padé, there's some parameter, some free parameter that you have. You have some choices in what Padé approximation you choose.
Even for field parameter, it may not be correct. It's just we just do that in numerical, and because it's an efficient method. But even for 3 parameter, 4 parameter, maybe make him a wrong answer.
Sure, indeed. So I mean that could happen. So the idea is that okay, you know perturbatively it's valid only at weak and strong coupling, and in between. This is one way of kind of getting an idea of what happens, but it's not like rigorous, like this should always be valid. I mean, Padé is an approximation. But okay, so they did this perturbative computation and a Padé approximation that they then nicely handed to me, and I put it in the bounds of the numerical bootstrap, and it's this black line that you see here. So we see that it's very close to the upper bound that we found with this soft sum rule. And this lower bound is if we set the gap to delta hat plus 0.5. If we increase it, if we take a bit of a bolder assumption and we set it to delta hat plus 1, we shrink it down to this kind of light green band that we see here. And this nicely encapsulates the Padé approximation. So, yeah.
Just a question about, so Bendegus gave you a Padé or many Padés, and if he gave you many Padés, then how sensitive are your bounds to the different Padés?
Yeah, so he gave me many Padés, infinitely many for a parameter k.
Yeah.
This is I mean, I can say the number, it doesn't make much sense.
Sure,
it's 1.9. So this is for one specific number, so it fluctuates a bit. And there's some that are kind of closer to the top boundary, some that are lower.
But does some value of this kappa parameter, does it break the bootstrap in some sense? So can you put...
There are some values for which this Padé approximation is going to show some poles, etc. Yes.
So no, but that's a Padé problem, I'm saying.
Exactly. So there's no, I checked and there's no one that kind of oscillates outside of these.
Okay,
these
so
bounds.
all Padés are consistent.
Yes, yeah.
So you can't use your method to break, to give some general thing.
No, indeed. Yeah,
okay.
yeah. Okay, and this is if we compare it to the bound on the displacement normalization. Okay, so we were very happy with this. This was kind of a surprise that it matched so well and it was so close to saturating the bound. But this also shows that in this case, this interpolation between weak and strong coupling seems, it has some extra kind of motivation. Okay, so now in the last 10 minutes, let me say something about what happens if you also have bulk operators and not only defect operators. So as we saw just 1.5 hours ago, there's more defect CFT data that we have now not considered, and one especially important one is this coefficient that appears in the bulk to defect expansion of bulk operators. So in the previous talk they were called B, here I call them mu. And if this first operator is the identity, this would give you the 1-point function of the coefficient that appeared in Marco's bootstrap setup. And now we can construct a 3-point function of 1 bulk and 2 defect operators that depends on a single cross ratio. So this cross ratio we now denote by omega. And again here y is the distance to the defect. And all these x hats are just the coordinates along the defect. So we also can derive integrated constraints. So the first one is with the soft identity. We take a single bulk field and a charge, and we get this constraint, and now we don't have to push anything to the defect. And we can actually just do this integral because this 2-point function is kinematically fixed. And this gives a relation between the 1-point function and the bulk to defect OP coefficient of the tilt. And okay, this was already computed in the literature, and it agrees very nicely. So now we can do the same thing for the 3-point function. So we insert one additional current, J, and another kind of scalar field, phi, and we can relate it to this 2-point function here. And then we only push J to the boundary now. So we leave phi 1 in the bulk, and we just push J to the boundary, and we get a constraint on the 3-point function between bulk, tilt, and tilt that we find here. Again, we can rewrite it in terms of this cross ratio, and we get a formula that maybe looks a bit nicer. And we can do the same expansion in terms of conformal blocks, where we now have these bulk to defect OP coefficients and the defect OPs. So we want to do the same trick, and we want to use another dispersion relation. So this, for this particular configuration, was derived in this paper. And now this is the discontinuity, but it's just a single discontinuity. So we don't have access to the double discontinuity. And this will mean that we only have single zeros and not this nice double zero structure. But that's life. And we still find this nice sum rule here. And okay, kappa is now simple enough that it just fit on one line, so I also showed this here for you. And we can derive these kind of constraints for several values of this parameter alpha. And all it does in life is kind of start the place where these single zeros appear, it just moves it. So for alpha equals 1, you see that there is a pole at delta equals 1. This pole is fake, so there's actually going to be a contribution for delta equals 2. But 4, 6, 8 are all 0. Then if we push to higher alpha, dimension 4 also starts to contribute, etc. So okay, this we can do it in general. I just wanted to show off a little bit, but okay, let's go further. So let me skip this because of time, and let's go to the final example, which is going to be the half BPS line defect in n equals 4 super young males. So this is integrable in the large n limit, and these Wilson line breaks the following supergroup. So we start from PSU 2,2/4 to OSP 4*4, and these supergroups contain the 4-dimensional conformal group and the SO6 R symmetry group here, and break it to the 1-dimensional conformal group, the rotations around the defect, and the SO5 R symmetry. So this has the same pattern of like a 1-dimensional defect that breaks ON to ON minus 1. And we can use the same constraints. So since it's okay, now we have the stress tensor, and we have the flavor current, and we have also the supersymmetric current, and they now nicely arrange themselves into a single supermultiplet, which is called O20 prime. And also the defect operators, so the tilt, the displacino, and the displacement, they now sit together into a single protected supermultiplet that is called D1. So because of supersymmetry, we now kind of put all the constraints together, and this just gives you a single, for example, for 4-point functions, just a single crossing equation. So okay, we can combine it with the conformal bootstrap, etc. This was already done in this beautiful bootstrapability program, where they combined conformal bootstrap with integrability and also these integrated correlated constraints. So one important thing is that they knew the full spectrum of non-protected operators that appear in the displacement OP. And they also derived 2 integrated correlator constraints. And a linear combination of these is exactly the constraint on the 4 tilts that we saw before. And the other one is coming from considering some cost Wilson line that is more related to the integrability part. And in this case, these right-hand sides can be computed exactly. So we don't have to use perturbation theory, either with integrability, so this C, or localization. And this, okay, I thought my bounds were pretty nice, but these bounds are next level. You can see here, if you zoom in and zoom in and zoom in, that this is going to be an upper and lower bound on the OP coefficient of the first operator, and that is currently at 10 to the minus 8.
At the worst point.
At
the worst point.
At the worst point. Ah, I see. Okay,
Best
so
point
is minus 9 or higher?
14.
14, okay. Yeah.
That's because my spectrum is 14. If I increase spectrum, I think.
I see. Yeah. So this is, this is, okay, next level. And you can see here the comparison with weak coupling and strong coupling results. So, okay, they already did this. And now the idea is to also include bulk operators into this, this bootstrap for the 4-point function of displacement. And we want to include this stress tensor O20 prime that we saw before. So we can derive these constraints for O20 prime and the tilt. And in this case, also the right-hand sides are known by localization. And we can extract this bulk to defect OP coefficient. And we checked that it perfectly matches whatever is in the literature. And also for the 3-point function, you can derive a relation. And you can check it with perturbative results by Daniele, who is in the audience, Julien Marat, and by Xu. And this also nicely agrees. So now the next step, and it's good I have 3 minutes left, so this is onto the outlook part of the talk, is to combine it into some bootstrap setup. So we saw before this system by Marco, which contained the bulk OP, the bulk 4-point function, and then the bulk 2-point function in the presence of the defect. And here we have a bit of a complementary system where we want to consider the 4-point function on the defect, the 2-point function in the bulk, and now this bulk defect 3-point function to also make it a positive semi-definite system, which was also the goal of Marco's approach. So the problem here is that we have to give up crossing symmetry. This one has crossing symmetry, but all these other correlators do not. Here we are only picking one channel, and we are throwing the cross channel out. And this means that we have to constrain them in other ways. This is going to be the role in life of some rules coming from locality. The defects have some rules that we just derived. And to constrain this 2-point function, we can again use integrated correlators that arise from supersymmetric localization. And of course, we also know the spectral data. So this is going to be the next step that we want to put these defects of some rules to use. And okay, numerics is running, so keep posted.
Sorry, why in the 2-point function you don't use custom?
Yeah, so in this case, I'm only using the channel that goes to the defect. So I'm only using this one, where we have mu. So we have mu squared, and the other one, as you drew, this one that has lambda and a. This we cannot use because we have we cannot access lambda and a. Yeah. So maybe in the future we can combine our setups into one big. Okay, but I think in higher D it's tough to have the 1-point function. Yeah. Okay. Indeed. So this is the outlook, and okay, I've done everything for 1D, but you can do the same thing in higher dimensions. For these bulk defect correlators, it's very simple. It's very similar than for defects 4-point functions, the expressions change a bit, but okay, it's not that difficult. And yeah, that's what we wanted to do. So let me go to the summary of what I've said so far. So we have found some rules for defects breaking conformal, global, or supersymmetry, and this gives constraints on these 3 operators. Some of them were already known. I hope I didn't miss anyone here, but probably I did. And we derived these new 3-point bulk defect and higher dimensional sum rules. And this combination with analytic functionals made it such that we have some nice bounds, and we can have some ready-to-use sum rules for perturbation theory. Yeah, and this is some ideas. It's mainly based on doing more bootstrap, different correlation functions, different setups, different defects. And okay, we also want to finish this numerics for the n=4 case. So yeah. Thank you.
Thank you, Finn, for the wonderful talk. And are there further questions? Maybe a couple of quick ones. Okay, we've already had a few, and the schedule is tight, so let's thank Philine again. And